in this lecture we talk about induced modules, co-induced modules, and then Shapiro's lemma. So let us start with the definition of induced and co-induced modules. So say H is a subgroup of G and say M is an H module like this. So this H is a subgroup, so we can make this M into a G module, and that's precisely what the purpose of induced and co-induced modules is. So induced modules, you take this ZG ring and then you tensor it with M, and you obviously have to have a G action onto it. So the G acts on the first element. So this A lies in ZG. So A is an element of this. So ZA tensor with M. So co-induced module is these homomorphisms, set of homomorphisms from ZG to M. So again, these are H homomorphisms. Now again, we have to talk about the G action on it. So the G action of G comes inside A. So again, this A is an element of this ZH, and this phi is a set of homomorphisms. So you're given some phi acting on this going to M. So phi is a map going from here to here, and you're evaluating it on some element A, and now we are giving G action. Notice that G is going on this side. So notice that from here it is going to here. So acting from the right side. Now in some books the definitions are changed. So these two definitions are flipped. So for notation we are following Cohomology of Groups by Brown. So the Brown's famous book. And for some of the proofs we are going to follow Milne's note on class field theory. So in so this notation is for Brown, and in Milne's class field theory notes this is flipped. So co-induced becomes induced, induced becomes co-induced. But the context would be clear. So now in case H is a trivial group, then you just again have this, but now you consider X as an abelian group, and obviously you drop H and you tensor over Z. So now you have this. So this is ZG tensor with X, and co-induced is this. So same definition here. You're setting H as 1, but again you can make this a G module by doing standard process. So you can see that how this was probably the original definition to make something into a G module, and then it was extended here. Now the reason for confusion between these two is that if H has a finite index in G, then you have this isomorphism between induced and co-induced modules. So now let us come to the lemma, which will be crucial for proving Shapiro's lemma. So for every G module M and H module N, so this is for any G and H, so H does not have to be subgroup of G, but for our case H being a subgroup of G helps. H being a subgroup G helps. So we will see this. So you can have this lemma for a general case, but obviously in the definitions, because of the definitions, we have H as a subgroup of G. So say we want to prove this isomorphism. So homomorphisms from M to co-induced modules G, H, N is this homomorphism from M to N. So these becomes H homomorphisms. So G homomorphisms are same as H homomorphisms, where you can say H is a subgroup of G, and this co-induced module is just a set of homomorphisms again. So first of all, we want to parse through this definition, and because this is kind of common, you know, this co-induced you can think of as home again. So we have seen this home multiple times in different avatars. So this is important to understand that how such a morphism is constructed. So first thing to notice is that you have this co-induced, which is nothing but this home, so ZG to M. So you have to consider some G to M map. So this this map, so co-induced, so you have ZG to N. So this co-induced looks like this map, this thing, and then this entire thing should look like this triangle. So more precisely, so you're given a G homomorphism like this, alpha to this co-induced module. So you're given a element here alpha. So from corresponding to this alpha here, you want to have an element beta. So what is this element alpha? Alpha is a map from M to co-induced module, map from alpha to co-induced module. So this co-induced is again a map. So this co-induced modules is some map from ZG to N. So let us just write it as this map G to N. So this is the map G to N. So this is the co-induced part, and corresponding to this we want to define a beta which will give us a map from M to N. So this is the beta. So this was a co-induced map which goes to beta. So the way to think about it is to draw these triangles here, and we have seen in algebraic topology, and this is our standard crutch, that homomorphisms from Z to Z is just Z. So that is, you have this group homomorphism from Z to Z. It is determined by multiplication by any integer n. So since you can vary n, you can get as many homomorphisms as there are integers, because any homomorphism from Z to Z is just multiplication by an integer. The total set is Z. So idea is, you every time what you're thinking is, where is 1 landing to? When you do multiplication by n, you see where does 1 land to. So 1 lands to, if you do multiply by n, lands to n. And that is it. You keep changing where 1 lands to. That is what multiplication means. You get a different homomorphism every time. Same strategy is used here. You see, where does 1g land to? 1g lands to m. So corresponding to m, some m, you have to have two maps. One is beta m, one is alpha m. And this is the only thing which you need to understand, that how to construct such maps. Every time you see such a map, home something, then home, means that you have to construct a triangle like this and make the triangle work. So the only easiest thing, or the only thing which we know from just looking at integers, is that where does 1 land to? So 1 lands to some element m here. So then you have two maps, beta m here and alpha m here, and they have to agree. And that's what we write here, beta m. So this beta m, you can write it as beta m. So this lemma actually has been taken from Milne's class field theory notes. So you can check it out there. So here you have alpha. So this beta you can think of as beta m, but we are writing small m here because it's easier. So this is beta m, maps to some element here, should be same as this alpha m acting on 1g. So basically this diagram we are copying right here. Now we are talking about g action, so you have to incorporate g action. So 1g can map to gm. So then by our definition, you have beta gm here, alpha gm here. Again, the g action is that this alpha gm, this you can actually think of as alpha gm. So this g can come out here, and this g can come out here. Although see, this n is a h module, so this g only makes sense if g is an element of h. So that's why I was saying it helps in our case to have this h as a subgroup of g. So now let us write this down. So what does this mean? So this is our definition. From alpha given here, we are going to beta here. So beta gm should be, so instead of m you have gm. So you have gm here. So this definition we have copied as such right here. So now this, because of the group action, comes out, but now this can go inside here and multiply with 1g. So now this equality comes from right here. So this thing is coming right here. So g multiplied by this on this side becomes this alpha m of g. So last equality form follows from the definition of co-induction. So when g is an element of h, we have from the diagram alpha mg is equal to beta gm by the series of inequalities. This is equal to g beta m. Obviously this multiplication by g will make sense going into n, because beta m is, so this beta m is getting mapped to some element n here. So this beta m, or we are writing beta subscript m, is getting mapped to some element n here, and you have to have a g action. So g action would only make sense if g is an element of h. So because it's g times n, so making beta into an h homomorphism. So you've gone from alpha, which was a g homomorphism, to beta, which is a H homomorphism, just by looking at the diagrams and thinking about the G action. Obviously for the reverse map you do the same thing but reverse. So now you can go from this beta, which is a H homomorphism, to alpha, and alpha has to go from M to again co-induced maps here by setting again the same thing. Alpha M of G should be defined as beta GM, because this obviously then G gets filtered out, which will make alpha a G homomorphism. So from an H homomorphism it has become a G homomorphism. So again in Milne this is written as induced, but here we are using the definition of co-induced. So after this lemma we can easily prove Shapiro's lemma. So Shapiro's lemma says that the cohomology groups, so now this H is a subgroup of G, and this is the homology and the cohomology group. So homology groups you can compute via induced modules, via this tensor product, and the cohomology groups you can compute via co-induced modules. So you know something about G, you can talk about a smaller subgroup H by just using induced and co-induced modules. So this be a standard projective resolution of G by Z modules. Then we have this isomorphism. So this isomorphism is just the property of tensor products. So once you have that property of tensor products, you take the homology of this side, you get this. You take homology of this chain complex here, you get this. And this homomorphism we get from here. So this is precisely the homomorphism which is here. So instead of M you have PI here. So instead of M you have PI here. And instead of N we have M. So instead of N we have M. So that is it. So this is here. This equality comes from precisely this equality here. And now you take cohomology here. You take cohomology of this side, you get this. You take cohomology of this side, you get this. And that is Shapiro's lemma.